Hello, my name is John Cody. I'm an engineer from Vancouver, Canada, and today I will be going over a proof of the quadrea of the projective quadrangle in universal hyperbolic geometry. This is a discovery I made and I detailed in a previous video. And in this video, I will be going through a Mathematica file, notebook, to show you the proof of this theorem, the quadrea of the projective quadrangle. Okay, so here's the setting. We're in universal hyperbolic geometry, and this is the projective plane with the null circle. Here we have four projective points, A1, A2, A3, and A4. We have quadrances between the points, Q1, Q2, Q3, Q4, and the spreads between the lines, S1, S2, S3, S4, and the quadrea is a the quadrea of the projective quadrangle is a projectively invariant quantity. Okay, so in the previous video I mentioned that there are the quadrea of the projective quadrangle is given by this pair of quadratic equations in A. And I stated that these two quadratic equations 1 and 2 are compatible, and meaning they have a common solution, and that common solution is given by this expression right here. Okay, just a bit of review. The proof makes use of the quadratic compatibility theorem, which is theorem 1 in the book Divine Proportions by Norman Wildberger. And it states that two quadratic equations, x minus p1 squared equals r1 and x minus p2 squared equals r2, these are compatible precisely when this expression is true. p1 minus p2 squared minus r1 plus r2, all of this squared equals 4 times r1 times r2. And in the case when P1 minus is not equal to P2, when P1 does not equal to P2, then there is a unique common solution given by x equals P1 plus P2 over 2 minus R1 minus R2 divided by 2 P1 minus P2. Okay, so what I'm going to do here is I'm going to create a Mathematica function for the unique common solution of a pair of compatible quadratic equations. So it's this equation here, and here it is in Mathematica. It's x, the equation we're creating is x is p1, r1, p2, r2. We pass in these four parameters, and is equal to p1 plus p2 divided by 2 minus r1 minus r2 divided by 2 times p1 minus p2. It's just this equation here, written out in Mathematica. And for these quantities, for P1, P2, R1, and R2, we're going to substitute in the values here. For P1, it's this quantity here. For P2, it's this quantity here. For R1, it's the right-hand side of equation 1, and for R2, it's the right-hand side of equation 2. So here's the function we defined, and we're going to pass in the P1. This is P1 here. This quantity here is R1. That's the right-hand side of equation 1. This is P2. That's the third parameter, and the fourth parameter is the right-hand side of equation 2. And that will give us the common solution, which we are calling A. A for quadrea of the projective quadrangle. And this is the value, the expression that's returned when we execute the cell. Okay, so again we have a projective quadrangle A1, A2, A3, A4 with side quadrances Q1, Q2, Q3, Q4, spreads S1, S2, S3, S4, and the quantity we're interested in is A. So here I'm going to, from the previous video, I said the quadrea of the projective quadrangle theorem. So suppose which states that suppose A1, A2, A3, and A4, that's these are distinct projective points with quadrances Q1 equals Q between A1 and A2, Q2, the quadrants between A2 and A3, Q3, the quadrants between A3 and A4, and quadrants Q4, the quadrants between A4 and A1, and spreads S1, the spread between the line A1, A4 and the line A1, A2. S2 is the spread between A1, A2 and A2, A3. S3 is the spread between lines A2, A3 and A3, A4, and similarly S4 is the spread between A3, A4 and lines A4, A1. And Quadrea A. Then the claim is that the quadrea of the projective quadrangle is the common solution of the following pair of quadratic equations. So here are the two quadratic equations. So the proof employs the quadratic compatibility theorem. We will show that these two equations are compatible since they meet the criteria for being compatible from the quadratic compatibility theorem. So we're going to be looking at, and specifically, this is the quadratic compatibility theorem. They're compatible precisely when this statement is true, when this expression is true. P1 minus P2 squared minus R1 plus R2, all of that squared equals 4 times R1 times R2. Okay, so the left-hand side of that, we get P1 minus P2 squared minus R1 minus R2, all of that in brackets squared. The right-hand side is 4 times R1 times R2. So I'm going to assign the value the left-hand side. I'm going to call this function with P1, R1, P2, and R2, and I'll get this expression here. So the left-hand side is this expression. And the right-hand side, we're going to call the function compatibility check right-hand side with the same 4 parameters, and we get this expression right here. Next, we're going to take our left-hand side here, which is this, and we're going to expand it all out. So we're calling the expand function from Mathematica, and so the left-hand side becomes all of this. So this is the left-hand side expanded. The E on the end stands for expanded. So here it is. It's this long expression here in the quadrances and spreads of the projective quadrangle. We're going to do the same thing with the right-hand side. We're going to expand right-hand side and get the expanded expression, and that's this. The right-hand side expanded out. Then we're going to take the left-hand side expanded out and subtract the right-hand side expanded out and get this result here. So this is the result of the left-hand side and the right-hand side all expanded out. It's this long expression in all the quadrances and spreads of the our projective quadrangle. Okay, next we're going to take our projective points, A1, which is x1, y1, z1. These are proportions. A2 is the proportion x2 to y2 to z2. A3 is the proportion x3, y3 to z3. And A4 is the proportion x4, y4 to z4. And we're going to define 3 functions for the join of 2 projective points, the quadrants between 2 projective points, and the spread between 2 projective lines. So the join of 2 projective points gives a line, and that's given by this expression here. It's A1, the second parameter of A1 times the third parameter of A2. So that'd be y1 z A2, Z3, yeah, Z2 minus Z1 Y2, or yeah, Z1 Y2. So these A1 and A2 are the X and Y's and Z of these 2 points that are passed in as parameters. Similarly, we have this expression for the quadrants between 2 projective points, A1 and A2. It's given by this expression. And the spread between 2 lines is pretty much the same expression. So here we have, we will call these functions we defined here to calculate the quadrants and spreads in terms of the X and the Y's and the Z's. So Q1 is the quadrants between A1 and A2. Q2 is the quadrants between A2 and A3. Q3 is the quadrants between A3 and A4. And Q4 is the quadrants between A4 and A1. And when we execute that, we get these results right here. So this is Q1. This is the expression for Q2 in terms of X, Y's, and Z's. This is Q3 in terms of X, Y's, and Z's. And this is Q4 in terms of X, Y's, and Z's. Next, we will calculate the lines L1, L2, L3, L4. L1 is the join between A1 and A2. We have projective points. We take the join between projective points A1 and A2. That gives us a line, so that's L1. L2 is the join between projective points A2, A3. L3 is the join between projective points A3, A4. And L4 is the join between projective points A4 and A1. And when we execute these statements, we get these results here. This is L1, this is L2, this is L3, and this is L4. Finally, we calculate the spreads. S1 is the spread between line L4 and L1. S2 is the spread between L1 and L2. S3 is the spread between line L2 and L3. And S4 is the spread between L3 and L4. And when we execute these functions, we get the expressions for the spreads in terms of the X and the Y's and the Z's. So this is the expression for S1. This is the expression for S2. This is the expression for S3. And this is the expression for S4 down here. Okay. So what we're going to do now, we had that expression for the results when we subtracted the left-hand side from the right-hand side. This was our result. Left-hand side minus right-hand side gave us this long expression. Now for each one of these Q's and S's, we're going to substitute in the expressions for those in terms of the X's and the Y's and the Z's. So that'll be our result now with X in terms of X and Y's and Z's, and we're going to factor all that. And when we do that, factorization, factor is a Mathematica function we can call. When we do that factorization, it comes out as 0. So the left-hand side minus the right-hand side came out to precisely 0. And that proves that, so we have, with that result, when that is 0, that means the criteria for these 2 quadratic equations being compatible has been satisfied or has been met. So therefore, we have proved that the following 2 quadratic equations in A are compatible. Equation 1 and equation 2 are compatible. And that's the result. In part 2 of this video, of the video series, I'm going to substitute in our value for A into this expression and show that indeed this expression here is also true. Okay, thank you.